Oh, check one. There we go. There we go. Hello, Disney Joe. And for a quick peek at the conditions outside, there's what we've got right now. The weather forecasters were predicting that the large band, here's the low pressure out here, you can see it. They were predicting that the bands would be further to the east, so that Rhode Island and eastern Connecticut would get hit, and they were saying, yeah, we're going to have some heavy bands of snow. Well, if you look at this band of snow right here, this has been over top of us in western Connecticut all day long. And let's see, right about here marks the spot. We've got an honest 8 to 10 inches of snow out there right now, and it's not done yet. We're not going to see the end of this until probably close to 6, 7 o'clock before it starts to taper off. Can't hang long, too long, but what? So let's see, here's the spare cam. I can just take the spare cam off the mount here for a second. Point it out the window. Give you an idea of what it looks like outside right now. It's kind of hard to tell. That cable dangling in the breeze is my coax going up to the antenna. So at least I know my antenna is still up. And you can almost see the snow coming down. Kind of hard with this camera at this resolution, but that's what we got going on outside right now. I'm doing my best to keep up with the snow on the deck. I'm at work. I took the day off. Anyhow, I have a couple of adjustments to make on the circuit here. The dead time between the two phases is a little bit too long. So I need to make a small adjustment to the ground resistor that's attached to pin 4, which is the dead time control. So let's see what changing that value does. I don't know which direction I need to go. My original schematic diagram showed a 12K. handwritten diagram showed 1K. I ended up using 1K. There's 10K. Let's see what that does. Not much. Man, that wind is howling out there. Turn to rain there, huh? Wow. I hope it doesn't do that here, because what a mess that's going to be. Yeah, definitely don't like that. It's kind of an interesting video that Ortoria sent me a link to about the fake breadboards, or the really cheaply manufactured breadboards that are being sold on eBay. Kind of makes me think it would be worthwhile just to rebuild the one that I've got, like I did not want to do originally. has almost no effect at all. Shorting it to ground reduces the dead time altogether. Where does that come from? Let's see, that comes from that capacitor, which also has no bearing on it. CT, yeah. I don't know. Kind of makes no sense. So 1K equals minimal dead time. 1K is, to this circuit, is close to a short circuit as it needs to be. Barely noticeable difference between 1K and a 10K. Wonder if I lowered the frequency. What is the frequency? Looks like my frequency is 2 microseconds, so that's 2. (10, 12, 14, 15 microseconds. Point 00 0015, right? 1 microsecond is 0.5 zeros and a 1. 10 is 0.4 zeros and a 1. 15 is point. Okay. So 1 over x. Where's my 1 over x? Right there. So it looks like I've got an oscillating frequency of 66.666666, sign of the devil, kilohertz. Which is pretty close to my operating frequency. So I'm right in the ballpark. That's good. All right. My actual operating frequency is 54 kilohertz. I need my clock frequency to be set higher than the master clock input sync. So yeah, I think that's going to do just fine. S11E01, okay, whatever that is. Did you look at the link I sent you for the process of growing crystals? I started to watch it. It's a little bit long. I have it on my watch later list. So yes, I will get around to that for sure. I have to say this, I might be tempted to buy one of those new breadboards anyway, simply because the ones that I'm using here are very old school, and they do not have the double power supply rail on either side, on each side of the breadboard, which, as I looked at it, thought to myself, gee, that looks handy. Pin 6, 10K. Oh, that's my oscillator resistor. Okay. And this is a 10K potentiometer. Excellent. So I can control my frequency with this. Here we go. 182. That's what I want right there. Why are we seeing weather radar? Is this another storm brewing? No, this is the storm that's on top of us right now. What you got there, 2 circuits parallel for 220. What I've got is 240 volt split phase. Standard house wiring. So what I did was on, yeah, let me show you. Over here on the wall, I've got a couple of quad boxes, right? There's a quad box there, and there's a quad box here. I've got 240 split phase coming down from the house, 30 amp service, and the way I wired it, I have 4 quad boxes along this wall. 2 of the quad boxes are over this bench, 2 of the quad boxes are over the far bench over here, and in between the quad boxes I have a 3-prong twist lock 240 volt outlet. So what I've got is I've got each of the quad boxes alternating on the phase coming in. So one side of the breaker box is has a breaker on that quad box, and that one repeats over there. The 2 right-hand quad boxes are tied together on the same side of the breaker box, and then the 2 left-hand quad boxes are tied together on the opposite side of the breaker box, and then the 240 volt outlets in between simply take their power from the 2 quad boxes. Now, it's not 3-phase or anything fancy, but it's enough to run a 240 volt welder if I ever get one, and it's enough to run my induction heater when I'm ready to test it. Which is the reason that I put it in that way. There we go. Now I have a full range of adjustment. So we've got 5 milliseconds per division. So we've got 50. Let's see, 5 milliseconds per division. So that's 5, 10, 15, 20, 25, 28 microseconds. So 0.000028 1 over x, 35 kilohertz. So I can adjust from 35 kilohertz pretty high. That's 100 kilohertz right there. And that's way higher than I need to go. There's 20 microseconds. So that's about 50 kilohertz right there. And I'll need to play with that when I'm testing the other part of the circuit that I need to build here. So anyway, let's start building that part of the circuit before I have to go up for dinner, eh? Two phase. No, single phase. Single phase with a center tap. Alright, so here's what we have to say about the master clock synchronization. This document is from Texas Instruments, so I believe it. Let's see, to synchronize the TL494 to an external clock, the internal oscillator can be used as a sawtooth pulse generator. Program the internal oscillator for a period that is 85 to 95% of the master clock, and strobe the internal oscillator through the timing resistor, see figure 20. Okay, so my timing resistor is connected to pin 6. And that timing resistor right now is a 10K resistor? Yes. It is a 10K resistor. Actually, it's variable. So this becomes variable. Okay, so that makes sense. That makes good sense. My computer is going to die soon. Sorry about that. Let's see, Q1 is turned on. Q1 is turned on when a positive pulse is applied to its base. That's correct. Q1 is turned on when a positive pulse is applied to its base. This initiates the internal oscillator by grounding RT, pulsing the base of Q2 low. Pulsing the base of Q2 low. Q1 is latched on. Q1 is latched on through the collector of Q2. And as a result, the internal oscillator is locked on. This goes low, this conducts, or this goes high. This conducts, this stays high and latches in the on position. That's correct. Good. So I understand that part of it. As CT charges, a positive voltage is developed across C1. As CT charges, a positive voltage is developed across C1. But this is already high. Q1 forms a clamp on the trigger side of C1. At the completion of the period of the internal oscillator, the timing capacitor is discharged to ground, and C1 drives the base of Q1 negative. So this voltage potential rises slowly. But when this goes to ground, that inverts the signal and releases Q1. Okay, at the completion of the period, the internal oscillator, timing capacitor is discharged to ground, and C1 drives the base of Q1 negative, causing Q1 and Q2 to turn off. With the latch of Q1, Q2 turned off, RT is open-circuited, and the internal oscillator is disabled until another trigger pulse is experienced. A common problem occurs during startup when synchronizing the power supply to a system clock. Startup when synchronizing the power supply to a system clock. Why does the power supply need to be synchronized to the system clock? Normally, an additional startup oscillator is required. Again, the internal oscillator can be used by modifying the previous circuit slightly. During power up, when the output voltage is low, during power up, when the output voltage is low, Q3 is biased on, causing Q1 to stay on and the internal oscillator to behave normally. Once the output voltage has increased sufficiently, where VO is greater than Vref, Q3 no longer is biased, and the Q1, Q2 latch becomes dependent on the trigger signal as previously discussed. I don't go inside laptops. Really? You don't? That surprises me. I do. Did you guys see my latest tweet about this new security bug? Man, is it windy outside. Holy shit. Not without, no, well, that's what YouTube University is for. Looks like the snow might be starting to break up just a little bit. Just a little. Which means I'll be out there with the snowblower in just a little while longer. I had replaced the HD in an ancient laptop. The, you know, to Asus's credit, the slim laptop that I just bought, the UX32 VD, awesome laptop. Awesome laptop. It's got 12 screws around the bottom perimeter. You take the 12 screws off, and the whole bottom half of the shell comes off. You have access to the wireless card, you have access to the hard drive, you have access to the battery. And hands down, the best laptop screen I've ever seen. The viewing angle on it is just phenomenal. You can view that screen from all angles, up and down and side to side. ASUS, Asus, Asus. I say Asus. Some people say Asus. And of course the snob over here is on a MacBook Pro. Because, you know, he's just got that kind of money kicking around. Alright, so the question is, what do I need for values? RT, and do I need Q3? My master oscillator is external. It should not need Q3. So I should be able to get by with this. The question is, Why would you not limit the base current with a resistor? Right there. And if CT is 0.0018 microfarads, or call it 0.002, then C1 should probably be 180 picofarads. Right? Probably don't want more than 1/2 milliamp flowing through Q2. So this would be, if Vref is +5, then 10K would give you 1/2 milliamp flowing through the emitter base junction. This also becomes 10K to latch Q1. And you probably don't want to pulse more than 1/2 milliamp, so all of these are 10K. Or thereabouts. So I need a PNP and an NPN. Check this out, my parts drawers are still labeled with Dymo label makers. Dymo labels. Shows you how old these things are. Can you guys hear that wind howling out there? That is not going to be fun to run the snowblower, I'll tell you that right now. I may just wait till tomorrow morning. Alright, so my NPN PNP choices. I have 2N4125. Oh, PNP, how about that? And 2N3415s. NPN. So we'll take a look at both of those specs, see how close they are. I would wait to do that till spring. Yeah, unfortunately I can't wait till spring. Alright, 2N3415, 2N4125. What do we got here? 30 volts emitter to collector, 25 volts emitter to collector, that's fine. Emitter base voltage 5, collector current 500 mils. Emitter base voltage 4, collector current 200 mils. $625 milliwatts dissipation, 625. How about the gain characteristics? HFE, small signal gain, minimum 180 on the 3415. Minimum 50. On the 4125, minimum 50, max 200. So the 3415 has more gain. NPN, PNP. I also have some TIS 98s and 93s. TIS 93 is a PNP. Wow, 800 milliamp collector current continuous. HFE 100. And also we've got a 2N4123. which is an NPN. $41.23 is $30.40 $200. Minimum 50, max 150. So I want, if I want matched, do I need matched? I don't think it matters. Nah. Who cares? All right. And then my leads. Go emitter base collector. I have no idea how I'm going to lay this out. The emitter of the PNP, which is the 4125, goes to VREF. VREF is 1314. Which is up there. So just for grins and giggles, let's just start plugging things in and see how things work out. Okay, emitter is connected to VREF. The base connects to the collector of Q1 through a 10K resistor. Emitter base Alright, so let's put Q1 on this side. The base connects to the collector, emitter base collector. So I'll insert this like that. It's getting cold in here without my miner running. Alright, so the base connects to the collector through a 10K. Emitter base collector the collector of Q2 connects to the base of Q1 through a 10K. Collector of Q2. So I need a jumper for 3 over there. No, that's 4. This is 3. Okay. So the collector, emitter base collector, the collector of Q2 connects to the base of Q1. The emitter of Q1 goes to ground. Check. The collector of Q1, emitter base collector, connects to RT. The collector of Q1. Maybe I want to flip that around. Yep. All right. So let me flip this around. And that faces like that. The emitter still goes to ground. All right, let's check this out again. Collector of Q1 connects to the base of Q2 through 10K. Collector of Q2 connects to the base of Q1 through 10K. Emitter to ground. Base of Q1 to RT. Base of Q1 to RT. Alright, here's RT. No. Collector of Q1 to RT. That's right. Collector of Q1 to RT. And RT jumpers to pin 6. One, 2, 3, 4, 5, 6, 7, 8. For heaven's sake. Collector of Q1 connects to RT and that 10K to the base of Q2. All right. The base of Q1, emitter base, receives How about that? 180 picofarads. All right. Moving right along here. The base of Q1 gets a second. Let's see, so emitter base gets 10K. With that, I leave you. Okay, bye. He usually builds on perf board and can jump from the underside. That's only after I know I have got a working circuit. I'm still amazed at that wind outside, boy. Wow. And there's my timing capacitor, my timing resistor. Timing resistor gets its ground through the collector. Right? Right. And then a diode. Diode isolated input. Okay. Make sure I have the polarity on that diode correct, because it's hard to see the band. Yep. Okay. Actually, I'll do this with a jumper. All right. If I've done my job correctly, the oscillator should start up again on its own with this jumper installed right here, which is the input trigger signal from D1 on the schematic diagram. If I disconnect it, it should wait for a pulse trigger to come in on that line. With the pulse train will come in from the master oscillator. Which will be the PLL. That's my story, and I'm sticking to it. So there's my clock input line. There's my scope probe jumpers. DC input voltage. All right, let's test it out. I do not want to go out there. I do not want to go out there. I forgot. What does the circuit do? It is a PWM regulator. The clock frequency, the clock signal has to come from the PLL. The PLL is the induction heater driver. That's controlled by phase lock loop. So the frequency is controlled by the induction heater PLL, but the duty cycle will be controlled by the pulse width modulator. And the frequency of the pulse width modulator output has to be slaved to the to the phase lock loop circuit. The phase lock loop has to be able to control the frequency, but the PLL controls the duty cycle. Alright. Power PWM variable temp, that's correct. He can be taught. Alright, look at that. I got signal. Yes, thanks. Don't mind me, I'm just being an asshole. Alright, so here's an example of the duty cycle. Right? But the frequency is that. So the induction heater will control the frequency. The PWM controls the duty cycle, but the frequency stays the same. Now if I yank this wire, it should stop. And it doesn't. Why doesn't it stop? Now watch this, start at 10 minutes, okay. Oh.
The total amount of electronic goods currently exported by Japan yearly is approximately 10 trillion 50 billion yen. That's the second largest income earner following automobile exports. From daily necessities to systems for specialists in physics, chemistry, metallurgy, and mechanical engineering. As a result, researchers were able to get their hands on highly pure crystals. Shortly after, William Fan developed his epoch-making germanium refining method. The discovery of this method, called zone refining, is a memorable event in the history of semiconductors.
Look at that, induction heaters.
This is a zone refining device reproduced for us by Tohoku University. We place low-purity germanium in a receptacle made of very high-purity carbon graphite. Seal it together with the receptacle inside a quartz tube and inject hydrogen gas. A copper heating tube is wrapped around the quartz tube and water is circulated through it so that it won't melt from the heat. This device is the same as a large microwave oven. When the high-frequency electric current sent from here flows into the coil, the germanium inside melts, and the impurities float to the top of the liquid surface. In this state, if we move the vessel slowly to the left, the impurities move to the right. When the heating coil forces the dirt to the surface, it is swept to the right edge. Then, if we chop off the right edge, the high-purity crystals are left behind. Thus, through the development of zone refining technology, it became possible for the first time to make germanium crystals with virtually no impurities. This is Gordon Teal, Bell Laboratories specialist on crystals. It was he who advocated that semiconductor material for transistors had to be single crystals. Here is an experiment of Gordon Teal. He made many trials and errors. As it was impossible to maintain the furnace temperature in a fixed manner, the crystals did not grow uniformly and resembled a succession of crooked carrots. The making of uniform single crystals finally came in 1948. We had the single crystal making process reenacted at Tohoku University. We placed germanium crystals with a raised degree of purity in a crucible, which we then set inside a furnace. We fit seed crystals for making them into single crystals to a rotating rod. We then seal the furnace and inject an inert gas. When we send a high-frequency electric current through the heating coil wrapped around the quartz tube, the germanium inside melts. Once the germanium has completely melted, we make the seed crystals contact the surface of the liquid while rotating them. If we make an error in the temperature of the liquid surface, the rotation speed of the seed crystals, or the speed at which the rotating rod is raised, the crystal drawing fails. The crystals melt if the temperature is too high, or if it is too low, they end up forming a crust. In 1954, the electronics department was established in the Electrotechnical Laboratory to spread semiconductor knowledge inside Japan through open research. The task of the two young researchers was to first purify crystals and then try to draw them into single crystals.
This was something revolutionary. What we were facing was the creation of a technology to make crystals with an unbelievable purity. And it had to be done by extracting the impurities inside the germanium. Neither we nor anyone else in Japan had this experience.
The vacuum furnace for drawing crystals took a lot of trouble to make, but if you fail to keep the error in the temperature of the melted germanium under plus or minus 1 degree, the crystals don't rise properly.
If the temperature gets too high when you hit the seed crystals from above, they melt away. And if the temperature is too low, they congeal and harden. That's also bad. Therefore, controlling the temperature is extremely important. Another important point is that when the temperature has been raised to almost 1,000 degrees centigrade, if you let the temperature act naturally, it rises and falls. That also is wrong. You have to keep the temperature fixed. Although I say fixed, there still is slight fluctuation. But this was kept at 0.1 degrees centigrade in the American specifications at the time. That's tremendous control. When the temperature rose, the needle of the gauge shook. We were unable to buy advanced American equipment. The temperature gauges at that time were rounder and bigger than this, and had a large needle. When we raised the temperature, this needle shot right up to 600 degrees, then 800 degrees, passing the melting point of germanium until it arrived at approximately 1,000 degrees centigrade. At that point, we lowered the temperature slightly. But as you can note, this needle mainly measures units of 1 degree, and 0.1 degree can't be seen. For that reason, no matter how many times you try, you'll fail at making crystals.
At that point, we attached a mirror to the base of the needle, and when we shined a light on it, the reflected light went all the way over and reflected on that wall. If we controlled the place reflected on the wall, if the width of the light expanded, the accuracy had increased. In any event, as it seemed to have become much larger, we tried experimenting with it.
This really went very well. At first, the reflected light hit the corner of the ceiling over there. Since I was in charge of drawing the crystals, I was fumbling with all sorts of things while peeking inside. Mr. Denda was swatting here in this vicinity. That's because of the resistor knob that changed...
Resourceful, that's what it is.
He was talking with me while looking at the image of the light. Then Mr. Denda would look at the ceiling, and when the point of light hit here, he would say, "Mr. Kikuchi, the temperature has dropped." We would then adjust the temperature until the light wouldn't come any further than here. By doing this, we made single crystals.
In 1955, when the Research Institute of Electrical Communications was founded at Tohoku University, a room was provided for Dr. Junichi Nishizawa, who was an assistant professor. However, because it was too small, the room was split into two levels. This is the laboratory which Mr. Nishizawa recorded with an 8mm camera. Researchers were often knocked unconscious after hitting their heads on beams. People called the Nishizawa laboratory the submarine. A giant transformer from which 3 thick cables extended dominated the room. In front of the cables, ordinary broadcast station equipment was set. This is a giant oscillator made by the laboratory staff, built entirely with discarded items they gathered. Unable to get their hands on resistors that could withstand a large current, they used hot plates instead. As for large volume capacitors that could withstand high voltage, they made them by packing oil into empty cans.
The amount of money we would use over the course of a year was usually 300,000 yen. With that 300,000 yen, we bought parts and built the oscillator. After that, what we did was for free, since it was our own effort. But there were some unpleasant things, like suddenly getting an electrical shock and being knocked unconscious. When I think about it now, I'm surprised no one was killed. There were occasions when I lost consciousness, fell to the floor, and later woke up.
Mr. Shingo Iwase, who is enthusiastically recreating an experiment from the days of his youth, is 72 years old. Mr. Iwase, who entered the National Research Institute of Electrical Communication after graduating from college in 1950, was ordered to do research on transistors. He began by making crystals. A quartz tube is fixed to a wooden frame. The inside of it is made into a vacuum by connecting a vacuum pump to remove the air. A copper heating coil, through which a strong, high-frequency current is sent, is wrapped around the quartz tube. At the time, the zone refining method had yet to appear. Mr. Iwase believed that if the germanium was melted slowly from the bottom up, then the impurities inside would gradually elevate, and at the clean portion remaining at the bottom would be usable. The problem was to raise the coil at a slow speed of several centimeters per hour. At that point, he hit on this device. When the water is slowly released from the bucket, this device lets the coil proportionately move slowly upward.
Things were different then. There was no golf to distract us. I worked almost around the clock. But since this was all new, it was exciting. And I was completely absorbed in my work.
That is exactly the same crucible method I will be using. Except instead of raising the coil, I'll be dropping the crucible.
Mr. Iwase was the first in Japan to succeed in making the point contact transistor seen here. This is the pocket radio, which incorporated that first Japanese transistor. After much trial and error, Japan finally had caught up to the level of making a point contact transistor. But by this time, the next generation transistor had already been developed in the United States. That was because the point contact transistor had a major drawback. This is the 2N104EH point contact transistor made by RCA of America, which actually went into mass production. However, production was stopped shortly afterwards because it couldn't stand up to practical use. The needles easily slipped out of position. They then tried firming the needles with resin. This is a test manufactured product sealed in plastic. Through the transparent resin, two needles contacting the small germanium crystals can be seen. However, due to changes in weather, the resin repeatedly expanded and contracted, and the needles finally slipped out of position. In the end, RCA abandoned mass production of the point contact transistor. The one who overcame this defect by proposing a needleless transistor, a junction transistor, was Bell Laboratories' William Shockley. He received the Nobel Prize for Physics in 1956, along with two colleagues, for the theory of this junction transistor.
All right, that's enough of that. And it's 5:30. All right, for some reason, this latch circuit will not unlatch for me, and I don't know why. Yeah. This is where breadboarding is invaluable. Anyway, I think that's going to be it for now. I'm going to start up the miner, try to maintain the temperature in here. I don't think it'll increase the temperature, but it will at least hopefully maintain it. We're down to 58 degrees now. And then when I come down here later, I will start up the rocket stove.